Good afternoon, all. And I'm going to talk about vPipe project. This project is a collaboration between with my advisors, Professors Ramana, Kompella, and Dongyan. We used a very provocative title because we couldn't find a shorter title which describes the our project in one line or something. So we focus on the applications which are I/O intensive in the cloud environment, and we can see many of the current cloud applications are very I/O intensive. Examples are web servers, data analytics applications such as Hadoop, and streaming media such as Netflix, and cloud storage. Although most of these applications are very different in their behavior and what the features they offer, we see one common characteristic in these applications. That is, they move data from one device or one location to another. That is, they copy or either move data from one place to another in most of these applications. So some examples are a web server hosting static files. The source is the file located in the disk, and the destination is the TCP socket connected to the client. And if the user uploading file to a cloud storage, the source is the socket that is connected to the client, and the destination is the disk or the storage, whatever the system backend. And the local file backup service such as rsync or something like that copies files from one disk to another disk or disk partition. And finally, a web proxy server or load balancer connects TCP sockets coming from a client connection to one of the backend servers. So some of these applications may involve processing while doing these data transfers, and some may not. But what we have found out is even in the applications that involve processing, there are steps in the processing flow that just moves data portions to one to another, such as Hadoop. It's a very processing intensive framework, but there's a part that just copies data from the mappers to reducers. Example is something like that. So let's look at a very simple example where a web server is hosting or sending a static file in the disk to a client. So in this case, the web server is hosted in a virtual machine monitor. I'm not sure why colors are not properly displaying in this case. It's supposed to have different colors. But so now the web server, basically when it gets the request, it looks up the file in the disk. And first, the programming a very simple program should look like this. So it first sends the HTTP header. It contains about information about the response and file, like file type and the file length. And then very basic programming would involve reading the data from disk in a tight loop and sending these disk blocks to the socket. So the data in this case would cross from disk to the disk to the VMM layer, or whatever the component in the VMM layer which is handling I/O, and then to the kernel layer in the VM, and then to the application, where application would copy or push the data to the socket, and it goes to the kernel and back to the network device. So there, as you can see, there are multiple layer crossings. In the normal operating systems without virtualization, there are optimizations such as send file, which cuts across one boundary here. Basically, it uses the send file system call or the function, which can shortcut these data copying operation at the kernel level of the VM. So in this case, the web server instructs or the program, the kernel, to shortcut the I/O operation. And what happens is it reads the disk, it goes to the VMM layer first, and then to the kernel, and the kernel does the copying, and then goes to the VMM, and finally to the network card. But even with this simple model, there are two main problems. When you have the virtualization layer, there is always going to be data crossing the VM boundary. So when there's data crossing, you have data being copied or some page sharing mechanism, and then we have the interrupt mechanism to notify the availability of data and to notify the completion of operations. All of these involve extra CPU overhead. And second, we have this in most cloud environments, VMs share CPUs, and this is because of the VM consolidation to increase the utilization and for power saving purposes. So in this case, the VM scheduling delays on the CPU can affect the I/O throughput, I/O latency, and hence the I/O throughput. In this case, when a device sends an I/O event to the driver domain or whatever the VMM layer or the component which is responsible for handling the I/O on behalf of the VM, the driver domain gets the I/O event first, and it goes to some shared location on the shared buffer or some shared bus or something like that. But at this time, the target VM may not be scheduled in the physical CPU, so it cannot process this I/O event. So when the VM gets scheduled in the CPU, it can process this I/O event and finally responds to this I/O event. But depending on this your VM scheduler and the degree of the consolidation, CPU consolidation in your system, the scheduling delay can be very significant, and hence the throughput of the I/O throughput can go down very much. So our solution to both of these problems is what we call the abstraction called the vPipe. So the key idea here is if the VM or the application doesn't touch the data, we don't even need to pull all the data to all the way to the VM. We can just shortcut the data path at the VMM layer itself. So by this way, we can avoid both data copying or layer crossing overhead, as well as VM scheduling delays. So let's look at how our web server example works in this case. So in this case, the web server has sent the header response first, and then it sends these programs very much similar to the send file system call. It's asked the kernel to do the shortcut operation, but this time the kernel asks the VMM layer to do the shortcut operation on behalf of it. Now, when the data so now the VMM layer can do the read from the disk and write to the network interface card. So this is our design of the vPipe system. Again, I'm not sure why the colors are not there, so everything looks similar. So now, in this case, we have three main components in the vPipe system. So the first component is the vPipe VM component, which interacts with the VM's TCP stack and the VM's file system to gather the information about the source and the destination of this data. So it interacts with it communicates with the user applications communicate with this vPipe VM component using the user API. A simple file in the /dev directory. Actually, we have written a wrapper around it, so the processors can just use simple function calls to interact with the vPipe VM component. Then we have a channel with shared pages. In Zen, this is a ring buffer and a standard device. And then finally, we have the vPipe driver domain component, which uses the virtual disk driver backend, which interacts with the image files and VMDK files and VMware terms. And then it uses the driver domain's TCP stack to offload the socket connections. I will talk about this what is this shadow TCP sockets in next few slides. And there are pool of threads which does the actual pipe operation on behalf of the VMs. So let's look at how vPipe offloads the file I/O. First, the application opens the file which is on the disk, and then it has a valid file descriptor, of course. Once it has the valid file descriptor, it pushes this file descriptor ID to the vPipe VM component. So the vPipe VM component contacts the VM's file system and requests the physical block IDs of this particular file. The file system, in turn, may go to the disk just to read the inodes, not the actual data blocks, but just a few inodes that corresponds to the file, if it's not already cached in the system. So it'll get this information, and it'll give an array of block IDs to the vPipe VM component. So once we have this vPipe, this block IDs, it can just transfer to the driver domain component using our channel. And now these block IDs because these block IDs are actually the physical block IDs, it can just use the standard read-write calls on the device to read-write files. And this is how we offload sockets or TCP connections to the driver domain in vPipe. So the application should first establish a connection using either accept system call, accept call, or connect call. So now it has a valid socket and a socket file descriptor. So it sends this socket file descriptor to the vPipe VM component, and it contacts the VM's TCP VM stack to get some information. So here, unlike the disk block case, we just don't try to parse the blocks at the VM, just the data blocks. Because what we do here is we offload the entire TCP socket to the driver domain. That is, we establish a shadow, a copy of the socket at the driver domain using the driver domain's TCP stack. And we fill out the source and destination information of the original socket in this shadow socket. So what we do here is in the driver domain, first we create a basic socket that has that doesn't have any information. And once the driver domain component gets this socket information, it fills those source destination IP addresses, port numbers, and sequence numbers and congestion information in that socket with the one given by the VM component. So now we have a shadow socket here. There's one more thing we need to do. We need to add a routing table entry to the driver domain's routing table so that the packets which are going to the VM that belongs to the connection gets routed to the shadow socket. So once we do that, we have fully functional socket at the driver domain layer. Now we can use some standard send receive operation at the driver domain to do the socket operation. Now we have this both file and socket working, so now you can do the shortcut operation. Basically, you can have a simple thread just engaging in a tighter loop, reading from the disk right into the file, or reading from the disk right into the socket, or reading from the socket right into the file, etc. So we implemented a very simple prototype on CEN 4.1 with Linux 3.2 for both the VMs and the driver domain. So for this, to implement this, we require support of all three layers involved in IO processing. Basically, the applications obviously has to use the vPipe system call or the vPipe call. And in the guest kernel, we use a loadable Linux kernel module as the to implement the vPipe VM component functionalities. And in the driver domain, also, we have a loadable Linux module to implement the vPipe driver domain component functionality. And we connect these two using a standard CEN ring buffer IO device. So our current prototype only supports socket file-to-socket operations, that you're sending a file in the disk to another client connected to you. But we are making very good progress on implementing the other three types of files as well. Actually, we have currently a working prototype. And we are also examining how we manage the fairness in the driver domain, because now every VM tries to offload their operations to the driver domain. Now we have to do some prioritization based on the VM's priority and manage proper proportional fair share at the driver domain. So in our testbed, we have 3 GHz Intel Xeon CPUs with 4 cores. For our experiments, since we have multiple cores, we just pinned the driver domain to 1 core. And when we have we experiment with multiple VMs sharing the same core, we just pin all the VMs to a single core because we want to see the VM sharing one CPU. All these machines are connected with gigabit Ethernet. For the very first experiment, what we did was we wrote a simple application which reads a file from the disk and just sends to a client which is located in some other machine, physical machine. So this application uses 3 modes. First, it uses the read-write standard, basic one. And then we have the send file system call. And finally, it uses vPipe system call. So in the first, so what we did was we sent a 1 gigabyte file to a client while varying the number of VMs sharing the CPU core from 1 to 4. So in the first case, when there's 1 VM running in the system, we don't see any difference because it's the only VM running in the system, and we don't see the actual overhead because this is the throughput. We don't see the CPU comparison. I'll show you the CPU graphs later, but right now the throughput can remain the same even though it consumes more CPU. So as we increase the number of active VMs sharing the CPU, we can see for both read-write and send file system, send file mechanisms, the throughput keeps on going down. But since we have offloaded the operation to the driver domain in the vPipe mode, the throughput remains same in all cases. So now we wanted to see how we fare in the CPU utilization with vPipe. So what we did was we looked at the previous case, the one VM case, and we transferred 1 gigabyte file. And when then we measured the overall CPU utilization, that is for both driver domain as well as the VM. The red bars here, the red components here shows the VM CPU utilization. As you can see, for read-write, it has the most amount of CPU consumption because you do the both kernel level and the application level processing. And for send file, you eliminate the application level processing because now you have the kernel shortcut, but it has still the kernel processes data. But for vPipe, we have the least amount because once you looked at the file, once you get the file blocks and the socket information and offloaded the operation to the driver domain, there's nothing has to be done at the VM context. And so now you might expect that the CPU utilization for vPipe should be higher for the driver domain, the blue bars here. But interestingly, we see a little bit savings about the little bit savings on CPU on the driver domain as well. So we wanted to see why we are having less CPU utilization at the driver domain as well, because the intuition tells you offload more operations to the driver domain, so the driver domain CPU utilization should go high. But then what we did was we did the same transfer, 1 gigabyte file transfer, but this time we looked at the CPU utilization of the I/O handling threads at the driver domain. So the blue components, blue bars here, represent the virtual disk drive access component, that is the loop in send terms. And it has to be, it is almost constant in this one because anyway, we have to read the blocks from the image file. So it doesn't matter where it's going to the VM or to the NIC, we have to read the blocks in this case. So the loop is almost constant. And we get a little bit savings because we do kind of optimized batching at the driver domain. So vPipe is a little bit lesser, but it's not that much less. And the red bars and the green bars, green or yellow bars here, actually represent the network backend emulation here. So that is for virtual machines, there is a backend component at the driver domain which emulates the different drives. For red one is the netback, which emulates the network card, and the green one is the blockback, which emulates the block device driver. None of these components are present in the vPipe case because we don't send any disk blocks for this operation to the VM, or we don't get any packets out of the network card during this operation. But someone has to do the transfer, so there's this vPipe main component which is doing the actual copy operation. And there are other small components such as soft IRQs or the other overhead operations which are almost constant in all three cases. So we do get some extra savings because we don't involve these netback and blockback threads. And for the final sort of application level evaluation, we adapted the very small application Lighty web server. Lighty actually uses send file for the sending static files. So what we did was we implement a similar library called vPipe file and replace these send file calls with the vPipe file calls. And our evaluation shows that vPipe with Lighty can achieve better performance than vPipe without Lighty. And finally, so we addressed the problem of virtualization affecting the, we talked about the problem of virtualization and VM consolidation affecting the throughput of the IO-intensive applications in cloud applications. So our solution, when applications are moving data from one location or one device to another, is to offload the complete operation to the driver domain, and then which reduces the data copying overhead as well as it avoids the VM scheduling delays. So our preliminary evaluation results in file transfer throughputs up to 2.4x, light throughput up to 3.9x, and CPU utilization savings, overall CPU utilization savings up to 38%. Thank you.
Hi, Konrad Miller from Karlsruhe. I think what you did here was you transported semantic of the send file call down to the hypervisor level and made it possible to use the send file through the abstraction layers.
Right.
Is that right?
For the first,
I think there's two things that you're actually gaining here. One is the copy loop. It's not in the user space, but in the kernel. Mm-hmm. And the second thing is that you're losing that you're getting rid of the copy operations.
Right.
So have you tried changing the I/O path of the VM to VM splice into memory and then splice to the network card? Because that would give you at least the copy part, get rid of the copy part.
Right. So I think the send file does that, right?
It does, but if you split it up that way, then you can transport the semantic down.
Oh, you mean...
it would be kind of an easy implementation of this vPipe. You just keep the semantic, the no-copy semantic.
Right, but yeah, I think that's an interesting idea, of course. But the problem right now, what we had is, when we do this splice still uses the sockets and the block information at the VM level. So most of the semantics are in the VM's file system layer or the VM's TCP stack.
Well, the read is translated to a virtual DMA request to the virtual device, and that is at the VMM level is translated to a I/O to a file with an actual DMA request to virtual memory, the virtual memory of the VM.
Right.
So you could actually do this without
I think for the disk, that's definitely doable. Yeah. For the TCP socket, I'm not 100% sure because now that's why we offloaded the entire socket as well, because you have to manage the sequence numbers and all this information. But if you have, I think I can definitely look at it later, but I think TCP has a little bit problems in this case.
Thank you.
Yeah.
Hi, Jay Kelly from HP Labs. This is great work for the important problem.
Thanks.
My question is, many vSwitches in hypervisor, they use something like maybe OpenFlow or QDisk or even maybe IP tables sitting in between the virtual machine and also the host operating system driver to do so many innovations.
Right.
Because now you bypass the past, do you have any idea how we can still leverage those existing tools sitting in between with vPipe?
Right. So yeah, that's one interesting problem. So even in this case, that's why we had to insert a routing entry to the VMM layer. But I see your point. So basically, the idea is you want to do vPipe operation after you apply all of these rules. Now you want to route your packets after you apply these firewall rules or whatever rules you have, QoS management rules, and then route to the driver domain's TCP stack. So once you do that, the driver domain sees the same set of packets or, after applying the rules. I think that might work.
Yeah, so I think I agree that might work for the routing problem, but what about rate limiting or shaping?
So even rate limiting. So let's apply the rate limiting before the vPipe operation, before going into before pumping into the VM. So we can shortcut that path, and say, once you drop the packet, whatever the remaining packets you deliver to the driver domain. So now you can do rate limiting as well.
Okay, thanks.
We can talk about it later if you want in detail.
The bar graphs that show the CPU utilization,
right?
Yeah, those I think are kind of revealing. I wonder how much of the time, how much of the performance you're gaining could be gained just by having more efficient device emulation, having a much lighter weight way for the guest and the VMM to do disks and networks.
I think you can save a lot. I think we used a basic, send device emulation layer. But if you have more, I think there's a talk in ADC as well regarding this, how to reduce the device emulation overhead. But I think you can, but you cannot completely eliminate. We are trying to completely eliminate it.
Yeah, I think
We
that-
haven't done any experiments on it because right now we couldn't find any,
I think the question is whether you could get enough of it to make it worthwhile, and whether it would be more attractive, therefore, not in effect for the guest not to have to explicitly hand things off to the VMM, because then things are a little more transparent for the guest. The guest just thinks it's talking to a simpler device.
Right. Yeah.
So it seems like there's some work to be done there to understand the trade-offs.
Right. Yeah, that makes a lot of sense because now we cannot use this vPipe with HVM guest, so guest that doesn't need any modification. We have to install all the way to we have to implement this all the way to up to application. So there is that trade-off we have to take care of.
Hi, Livio Soares from IBM Research.
Mm-hmm.
So for the file system case,
Mm-hmm.
you had to create, I'm going to call it a shadow inode of some sort. You had to pull down from one layer the layout of a file into the other layer.
Right.
And because I guess you have the file system in the upper layer. So I'm a little bit curious, what happens when either there's a modification in the original file, or another way to look at it is how do you implement file-to-file transfer, since the destination file is something also defined in the upper layer?
Oh, so that's what we're working on these days, how to do a file write or append or new file operation. So in this case, what we did was we have to actually now we have to modify the VM's file system a little bit. So in this case, what we do is in Linux, what we do is we provide what is called buffer heads to the file system layer attached with pages. And then the file, whatever the file system which is implemented, it will allocate more inodes. And now these buffer heads will be associated with the physical block numbers once the buffer heads come out of the file system interface. So that's what a regular write is. So what we did was here a little bit trick. Actually, we provide empty buffer heads to the file system layer. And in the file system layer, we just allocate a set of inodes. And we first flush these inodes to the disk, and then give the this buffer head information to the vPipe VM component. Now vPipe VM component has empty disk blocks in the disk, and IDs. There are IDs as in the array. So now you can do the write operation.